Hello, in this example, we're going to see how we can use Taylor series to approximate integrals. So we want to take the integral of 0 to 1 of e to the negative x squared dx. This is an integral that is very well known to not have an antiderivative, meaning we can't just directly compute this. No matter what, to compute this integral, we need a workaround. And the workaround we're going to use here is Taylor series. So we know the Taylor series of e to the x is equal to n equals 0 to infinity of x to the n over n factorial. This means if I put in negative x squared, this will be the series n equals 0 to infinity of negative x squared to the n over n factorial. Distributing that n exponent gives us the series n equals 0 to infinity of negative 1 to the n x to the 2n all over n factorial. So there is our series we want to work with. Meaning, now, if we take the integral from 0 to 1 of e to the negative x squared dx is equal to the integral from 0 to 1 of that series. The series n equals 0 to infinity of negative 1 to the n x to the 2n all over n factorial dx. And we saw back in the Taylor or the power series properties, I can integrate a power series by integrating just this term. And so integrating x to the 2n, that is equal to adding 1 to the exponent and then dividing by the 2n plus 1. And plus c for the antiderivative, making this the integral from 0 to 1. Well, once we take the integral, sorry, will be negative 1 to the n x to the 2n plus 1 over 2n plus 1. We just use the power rule on the x part and then n factorial. Evaluated from 0 to 1. This goes from n equals 0 to infinity. We can use the fundamental theorem of calculus on this. And we plug in our lower bound and upper bound. So plugging in the upper bound, we get negative 1 to the n, 1 to the 2n plus 1 over 2n plus 1 times n factorial minus, plugging in our lower bound, n equals 0 to infinity, negative 1 to the n, 0 to the 2n plus 1, all over 2n plus 1 times n factorial. This second series here has a 0 to a power. The whole thing ends up being 0 because every term is 0. And then this 1 to the 2n plus 1 is always 1. Because 1 to any power is 1. Meaning we have the series n equals 0 to infinity of negative 1 all over 2n plus 1 times n factorial. This is equal to, following this chain, the integral from 0 to 1 e to the negative x squared dx. So we have taken the integral. The last, or the second sentence is saying we just want to retain as many terms as needed to ensure the error is less than 1 over 10, and I'm going to change this to 10 to the third instead of 10 to the fourth. Process is the same, we'll just need fewer terms. So 10 to the third instead. This is now saying, I want to take this series I have found, and I want to approximate it. I want to approximate the series n equals 0 to infinity of -1 to the n over 2n plus 1 and factorial. Some of the wording here is ensure that the error is less than that, or less than 1 over 10 cubed. We have an error term. We are down to just a normal series. There is no x in here. So this isn't a power series anymore. This is just a normal series. And back in chapter 10, we had two theorems about the error term. We had, if it's an integral test, we can find the error to be between two integrals. And if it's an alternating series, we have a rule for the remainder. This is an alternating series, meaning we can use that remainder theorem. The remainder theorem says that the absolute value of the remainder for an alternating series is less than or equal to b sub n plus 1. In this case, b sub n is 1 over 2n plus 1 times n factorial. So we want our remainder, which is b sub n plus 1. That's going to be 1 over 2n plus 1 times n plus 1 factorial. And simplifying that out, that is 1 over 2n plus 3 times n plus 1 factorial. We want this remainder of our alternating series to be less than 1 over 10 to the third. We want strict less than. We want to find what does n have to be. That's just solving this inequality. The easiest way when there's a factorial is to plug in values. So if n equals 0, we'd get 1 over 3 times 1 factorial. This is 1/3. That is bigger than 1 over 1,000. So it's not n equals 0. N equals 1. We get 1 over 5 times 2 factorial. This is 1/10. Again, that's bigger than 1 over 1,000. When n equals 2, we'll have 1 over 7 times 3 factorial, which is 7 times 6, or 1 over 42. N equals 3 gives us 1 over 9 times 4 factorial. This is 4 times 24, which is 1 over 216, or 9 times 4 factorial 24, 1 over 216. Both of these still bigger than 1 over 1,000. And when n equals 4, we have 1 over 11 times 5 factorial. That is 11 times 120. just by estimation, we know that's going to be bigger, but if we actually calculate this out, this is 1 over 1,320, which is 1,320 is bigger than 1,000, so 1 over 1,320 is smaller than 1 over 1,000. So we need up to n equals 4. For our approximation to be big enough, or to be accurate enough. So going back to this line, we want to approximate it up to the 4th term. So I'm going to plug in these values. When n equals 0, we get 1 over 1 times 1. It's going to be 1. Plus, when n equals 1, we'll have negative 1 over 2 times 1 plus 1 is 3 times 1 factorial is 3. Plus, when n equals 2, we have 1 over 5 times 2 factorial, that's 10. If you notice, these are turning out to be the ones we've already calculated. So the next one would be plus a negative 1 over 42. And then plus 1 over 216. And there is our n equals 0, n equals 1, equals 2, n equals 3, and n equals 4. So the integral of e to the negative x squared between 0 and 1 is approximately whatever 1 plus negative 1/3 plus 1/10 minus 1 over 42 plus 1 over 216 would work out to be. So we can approximate this integral with reasonable accuracy by using Taylor series. So Taylor series become very useful as they ultimately are working with polynomials rather than functions that we might not be able to integrate or easily take a limit of. So Taylor series, very helpful.